Thank you for coming to Theory Lunch. Today we have Thomas. He will talk to us about efficient online random sampling. And also, this is Thomas speaking skills, so I'll have to ask everybody to go out after the talk finishes so that the committee can discuss. Thomas.
All right. Hello, everyone. I'm Thomas Draper here to talk to you about efficient algorithms for generating random numbers in an online problem setting using a technique called randomness recycling. This is joint work with my advisor, Faraz Assad, and I presented it last month at Sorel. So for an overview of what I'll be talking about, we'll begin with the problem of random sampling and some motivation and definition and generalization of the online setting, as well as some important metrics of efficiency for random sampling algorithms, particularly the entropy cost. With this background, we will be able to describe the main result, which is an exponential improvement in the ratio between entropy efficiency and space required compared to several previous works. After that, we will go into more detail about the technique of randomness recycling and then describe some experimental results showing that this is practical and can speed up real-world algorithms. And we will conclude with some future work. So now onto random sampling. Generating random numbers is a fundamental problem in computer science, and it is used in a variety of applied areas, including randomized algorithms, artificial intelligence, machine learning, as well as modeling and simulation. Generating random numbers has also been studied in the theory community, and some of the first algorithms for generating random numbers were proposed by John von Neumann in the 1950s. And 2 decades later, Donald Knuth and Andrew Yao developed much more thoroughly a theory of non-uniform random number generation, including entropy cost. And we study the problem from their perspective. So for the problem of random sampling, we can assume that we are given a probability distribution P over n different outcomes. And so our description of the probability distribution consists of the probabilities of each of these outcomes, as shown in this bar chart. And we can think of this as rolls of possibly loaded dice. And so we describe the goal of this problem is to generate an integer I with probability P of I. And we want an algorithm that does this, and generally algorithms will be seen as deterministic procedures, which would make it impossible to generate a random output. And therefore, we also need a random input to the algorithm in order to be able to generate this random output. We will take as our random input the fair coin flips. Or more formally, this is a sequence of independent and identically distributed Bernoulli 1/2 random variables. Informally, we can think of this random sampling problem as simulating a given loaded die using flips of a fair coin. In this problem setting, what we wish to minimize is primarily the expected number of coin flips consumed before producing our output random variable. This is also called the entropy cost. And just as with other algorithms, we also wish to minimize the expected runtime and memory space of our algorithm. We are only considering the problem of exact samples from a given distribution, and in general, if the probabilities are irrational, then you cannot do this with bounded memory, and it cannot therefore be implemented exactly on any finite space computer. So we restrict our attention to probability distributions where the probabilities are rational. This allows us to use deterministically bounded memory for our exact samplers. However, we still need to worry about expectation on the number of coin flips used, as well as the runtime of the algorithm, because we cannot, in general, provide a deterministic bound on this.
Can I ask a question?
Yes.
Even if it's irrational, can't you generate a solution that's bounded in expectation?
That's correct. It will be bounded in expectation, but because it's not deterministically bounded, if your machine has finite space, then if you go past that limit, then you're not producing a correct sample, and it's technically not an exact sampling
You,
algorithm.
you want to have it, abound on the number of coin flips that you're gonna use. And a priori, based on the distribution, you're gonna compute a bound on how many coin flips you need.
Actually, it's not a bound on the number of coin flips needed, just on the memory of the algorithm. Because
The
you don't
memory.
necessarily need to be storing like the number of coin flips you consumed, because in that case it could grow without bound. But you can consider this some like finite state automaton, where it's just consuming coin flips as you go.
Oh, so it's because a rational number can be written in a periodic pattern.
That's
in
correct.
binary or
Yes.
something.
Mhm.
Okay.
Mhm. And now in real-world workflows, instead of just generating samples from one distribution, we will want many samples from many different distributions. So we can define the online version of the problem as follows. We have a series of rounds I, and in each round we receive a probability distribution pi, and our goal is to generate a sample xi from that distribution. You can notice that compared to the previous slide, now the p's are uppercase because they can be random themselves. And in fact, they may depend on the previous xi's sampled in previous rounds of this algorithm. However, the correctness condition for this online random sampling is that conditioned on the input pi, the xi must be distributed as pi and independent of all the previous outputs from the algorithm. Now, if we compare this to the more basic random sampling problem, they share the inputs of the stream of coin flips as well as the description of the probability distribution, but in addition, at each round, our online random sampling algorithm has this auxiliary state, which we can think of as the program state carried over from the previous round. We will see that this allows us to improve the entropy efficiency of the algorithms. Similarly, in addition to producing the output sample value, we will also produce an updated auxiliary state after each round of this online random sampling. The overall flow of information in a given round is as shown in the top right here, where we have the probability distribution, we have some random coin flips, and we have an auxiliary state. And we produce that sample and updated state. Mathematically, we can say that an online random sampling algorithm is a computable function from sequences of bits and descriptions of probability distributions and our state space to samples from those distributions and updated states. With this distribution, or with this definition, we can also define the number of coin flips consumed in a given round I to be the random variable vi, and the total coin flips consumed so far is ti, the sum of the previous vj.
What is c greater than ti?
That's exactly what I'm going to talk about. Now, this is the same sequence of coin flips indexed to be greater than ti minus 1. So this...
So c is the sequence of your coin flips?
Yeah, we can assume that we have a single fixed sequence that we're using throughout this whole iterative procedure, and we index it to be greater than ti minus 1, which means that we're only considering fresh flips that have not been used in the previous rounds of the algorithm. And with this formulation, we see that the entire runtime of the program is a deterministic function of the single sequence of coin flips C, as well as the input distributions PI that we are asked to sample from. Now we'll consider some bounds on the number of coin flips that our random sampling algorithms can consume. For convenience of notation, we will return to the case that these distributions are fixed, but we can also generalize our results for when they are randomized. And we recall that we use Tn to represent the number of coin flips consumed to sample the first n outputs. Here, Knuth and Yao proved a lower bound on the entropy consumption of random sampling algorithms. They showed that the expected number of coin flips consumed by any correct random sampling algorithm for n different outputs is at least the sum of the Shannon entropies of those n distributions from which we sampled. The Shannon entropy is as defined down here, and we can think of it intuitively as the expected information content contained within a single sample from this distribution P. Therefore, this is a typical Shannon type information inequality where we see that the output random information in terms of these random samples cannot be any more than the input random information that we got from these coin flips. Yes?
But here you're allowing the PIs to be like correlated, or like, do you need like the PIs have to be completely?
Yeah, the generalized version where the PIs are randomized is a little bit more subtle, but basically we can say if the PIs are all random and can depend on the previous xi, then instead of just h of pi, this will be the expectation of h of pi. So yeah, it's just weaker in that we have expectations. But we can also prove a stronger bound where we condition on the output values and on these distributions, and then instead of these entropies, we have information content. But
so basically
it's kind of subtle.
your PI plus one have no dependence on like the outcome of the previous phase.
Yeah, that's right. Here, that's what we're using this lowercase p to represent, is that it's not a random variable, and it's just like fixed. And now we are ready to describe our main result, which is an exponential improvement in the entropy space trade-off compared to previous work. And we come, in some sense, epsilon close to this lower bound that we just saw. Here's a simplified version of the theorem statement. We let delta n sub d denote the set of rational probability distributions with denominator bounded by d. For any positive real number epsilon and positive integer d, we provide an online random sampling algorithm such that for every possible sequence of input distributions, p1, p2, etc., as long as these are rational distributions with denominator bounded by d, the expected number of coin tosses consumed by our algorithm is bounded by the entropy of the distributions we're sampling from, plus epsilon times the number of samples that we produce, plus a constant which just depends on the parameters d and epsilon. So we can think of this as, we know that the lower bound is at least here for the Knuth and Yao's theorem. So we're coming epsilon n close. And if instead we rearrange this as like the difference between what we consumed and what the lower bound was, and divide by the number of rounds n, then we end up having something asymptotic to epsilon. So in this sense, we can interpret this statement as saying we come epsilon close to this lower bound on the entropy rate. Right?
In this setting where the p's are fixed, are little p's, like, is there a reason to think of it in this way as opposed to just having like one giant probability distribution on like an n-tuple of numbers? Like there's the product distribution on p1 through pn.
I think this gives you the kind of simpler formulation of it, but like from this formulation, you can prove all the other more general versions of the problem.
Could you explain what the epsilon is doing? Is it an approximation term for how accurate your distribution is, or because you said your distributions are perfect?
Yeah, that's right. We are considering exact sampling, so this epsilon is just a parameter telling us how close we are to this optimal entropy rate, which was this lower bound that we saw for Shannon information. So we can say that we have some input epsilon that we want to be this entropy efficient, and if we want to be that efficient, then we generate some algorithm that requires some amount of space, where if you want a smaller epsilon, you need more space, and you'll have a kind of
so epsilon
slower.
determines the.
Yeah, that's right.
If you want to use less space, you have to have a bigger epsilon. You're not going to be as efficient.
Yeah.
In terms of the number of coin flips.
Yeah, all of this is
With
about
more space, you can be more efficient in
Mhm.
using fewer coin flips.
Yeah, there's this entropy space trade-off for online random sampling algorithms. What do you say?
Sorry, I just want to simplify your parameter space a little bit. So like if I think of like epsilon as 1 over n, does this work?
Yeah.
So you basically you just get like lots of like n.
Yeah. What's for real epsilon? And these algorithms that we are using, they use state space, which is asymptotic to 2 log d over epsilon bits, and the temporary space required during sampling is just big O of log D over epsilon. And our randomness recycling ideas work on several different samplers, and therefore our algorithm, we can use different configurations to achieve different combinations of sampling space and runtime, as we will see with later examples. So in short, our algorithm comes epsilon close to the optimal entropy rate while using O of log 1 over epsilon space. And we can compare this to some previous work by Kozen and Soloviev, as well as Shao and Wang. Both of them require O of 1 over epsilon space in order to achieve the same epsilon rate. And therefore, we have an exponential improvement over their work. We can also compare to more classical and mathematical theorems. Knuth and Yao derived the absolute entropy-optimal algorithm, and they showed that it comes within 2 of the total entropy of the output that we produce. And therefore, it achieves epsilon equals 0 as you're dividing by n the number of rounds, because this 2 difference is a constant, and yeah, it doesn't depend on the number of rounds. Similarly, Han and Hoshi proved that arithmetic coding uses an expectation at most 3 bits more than the entropy of all the distributions you've generated from so far. So this achieves the same epsilon equals 0 bound in the limit. However, an exact implementation of either of these two methods uses space and per sample runtime, which grows without bound as the number of samples, without bound as a function of the number of samples you have produced. And this growth without bound occurs even if you restrict the inputs to the distributions that have rational probabilities with bounded denominator, as in our problem setting. Uematsu and Lee also provided a finite space implementation of Han and Hoshi's interval method. However, they only give approximate samples, and to compare, we give exact samples, and we're focusing on the problem of exact sampling. Lastly, we note that stateless samplers, which don't carry over any state between the different rounds of sampling, cannot hope to achieve anything better than the rate of epsilon equals 2 by a theorem of Knuth and Yao. Therefore, we can think of our method with this epsilon parameter as a kind of interpolation between these stateless samplers, which don't require any extra space or information carried over between samples, and Knuth and Yao's entropy-optimal online method, which uses unbounded space but exactly achieves the entropy rate. And our interpolation is much better than previous work, which used significantly more space for a given entropy or had significantly worse entropy for a given level of space. Richard?
Sorry, I just want to clarify a couple of things, right? So for stateless sample, so I mean, I can definitely take your argument and rerun every step, right? At which point, basically, that would be like I require log D extra coin flips per step in expectation. Like if I just don't keep any state, I just rerun the whole thing, just by like taking more coins.
Yeah, that's correct. So with this constant over here, this constant is like ends up being at least 2, and Knuth and Yao proved that in the worst case you get 2 for even an entropy optimal algorithm. So if you do the same thing just every time, instead of like kind of batching together or like carrying over your information from round to round, then yeah, you can't do better than this like stateless sampling baseline with epsilon equals 2.
Wait, but like, I mean, isn't there some weird? I'm just going through the many parameters right now. This is kind of overloading me a little bit. But like, if I just set d equal to 1, or like I said, like I don't know, d equal to 2. Right? Every step I just flip my coin. How does that interact with the Knuth-Yao bound? Right? Because that just every step I flip 1 coin.
Oh, if you're like considering how that bound works on this set of possible distributions, then yeah, actually if d is equal to 2 and you're only generating these fair coin tosses, then you can do it without any entropy loss. But in general, as d scales, then you cannot make the same guarantee.
Okay, so the guarantee of Knuth-Yao is that, I mean, I think just in general, but with lower bounds, it's just there's like a lot of qualifiers involved. I'm just trying to figure out what are the qualifiers. So it's,
yeah.
You need Okay, so basically you're saying that to keep the overhead, so you need at least 2n plus log b bits if you keep no state.
Yeah, if you keep no state, then in the worst case, if you're getting like bad probability distributions, then you can't do any better than the sum of the entropies plus roughly 2n instead of this epsilon. That's correct. That's what I was meaning with this. Epsilon equals 2 is like that linear factor has like 2 multiplying that in there. All right, now we are ready to describe more of the details of this technique, which we call randomness recycling. So here is an example of a basic sampler which is completely stateless and it has no randomness recycling, nothing carried over between rounds. Instead, in each round we draw fresh coin flips from the entropy source, we transform them into a uniform random variable over a given range, and then we apply a deterministic transformation, such as the inversion method or alias method, and using this, we are able to achieve this output sample over exactly the desired target distribution. In practice, we will choose this uniform usually to be over the range corresponding to the denominator of our distribution, which allows us to get this exact sample. Now, our contribution with randomness recycling follows this same basic structure, but we add a recycling loop. Here, we take the convention that all of our recycled random information will be given as uniform random states. We define this to be a pair of integers, z and m, such that conditioned on the value of m, z is distributed uniformly over the integers from 0 to m-1 inclusive. Now, this might look like a real continuous interval, but since we are only considering discrete problems and things that you can run exactly on a finite computer, we use this notation just to represent the integers in this range, from 0 up to m-1 inclusive. As you can see in the diagram, we modified the original uniform sampler to also produce this output, which is z star m star. And similarly, we modify this non-uniform sampler to produce its own discrete uniform random state. We can think of these as capturing the input random information, which was not needed to generate these primary outputs of ui and xi. But this is still useful and independent random information, which we can use in later samples without becoming correlated with these values ui.
Well, Z star, M star don't get used for just the i sample, right? You could just ignore them when you're producing the i sample, is that right? At least from this picture.
Yeah, that's right.
So
These
why,
only improve the entropy efficiency when you feed it back into future rounds.
but why don't you just like regard them as randomness from a future round?
What do you mean?
Why don't you, like, why do they even appear the round before then? If you're just gonna use them in future rounds, like, it's
Because you need to like compute them and store them to pass them on to the future rounds. This is what we're doing with like maintaining this state across rounds. If you're not being careful to compute this in some way and ensuring that it's independent and then passing it on to the future rounds, then it'll just be lost information. So yeah, all this recycled information, we're just keeping track of it for use in future rounds, because that's the only way we'll be able to have access through it, is through this this auxiliary state that's carried over from round to round with the algorithm.
so I can't just regard Z star and M star as like being generated in the round that I'm using them. They have to be like somehow generated from the coin flips from previous rounds. This is like an important distinction.
Or the Z star and M star are coming out of the uniform, and the Z prime M prime are coming out of this sampler, and then we have another merged Zi Mi, and this is what we're thinking of. This Zi Mi is exactly passed across between the rounds.
Okay.
Yeah.
Can I ask a more basic question?
Mhm.
Sorry, I don't want, but, so if the distribution you wanted was a uniform distribution, so where did that extra, I guess I'm not seeing where the extra information comes from, because.
Yeah, we'll work out some examples later.
Okay, but this is a much more elementary question than all the questions you've been answering to other people, right?
Yeah, well, I guess It's because for our method, we actually end up using much more input information than is needed just to generate this uniform. And that's why we have some extra information left over that we can put into this uniform output.
Okay, but is there extra information going from the uniform to the specific distribution? Does that contain extra information or no? It's not working.
Yeah, also in this non-uniform sampler, the input uniform contains more information than this non-uniform sampler.
Yeah, okay.
So that's why we have this
That's
extra.
part of where it comes from, but it also comes from the very beginning phase.
Yeah, that's right.
Okay.
Because here we'll end up drawing more coin flips than we need just to be able to make this uniform UI, which will allow us to make the overall process more entropy efficient by having this efficient recycling with these uniform random states. And we can take this recycled information from the uniform and non-uniform sampling procedures and merge them with a simple rule, which is just multiplying and adding them together. And then we get a uniform over a range, which is the product of the individual ranges. And we can also think of this as if you have the two uniforms and put them on like orthogonal edges of a rectangle, then we have a uniform over like all the indices within the rectangle. So this is kind of like a way of pairing together two independent uniforms to get a uniform over more states. And this simple rule is one of the main reasons why we take the convention that our recycled uniform or our recycled information is these uniform random states, because they're nice to work with. They provide like a fast implementation also. And once we have done this merging, we'll have this single ZI-MI, which we can then feed back into the next round, which reduces the overall entropy cost. Now we'll take a look at some of the details of this merging procedure and how we can work with uniform random states. So in an imperative programming language, we can take some global state consisting of two integer variables, z and m. We will initialize these to 0 and 1 because this is the unit type, a uniform over just one outcome. And this is the only valid initialization or deterministic initialization of a uniform state. Now we can write the merging procedure we saw before instead as a recycle operation, where instead of thinking we have these two inputs and one output, we can just consider it as we have this one input and we're updating this global state using the same merging rule for more imperative style. And one way we can apply this recycling procedure is if we want to recycle in randomness from the entropy source of these coin tosses. So here we call our procedure refill, and we think of W as the word size. This is what we want to be the number of bits in our integers. So the goal of this procedure is to ensure that M is in the range from 2 to the W minus 1 to 2 to the W. This means that it's like the largest possible W bit integer that you can make it, where doubling it wouldn't overflow a W bit integer. So in order to do this, we first compute the number of fresh flips we'll need in order to achieve this bound, and we can do this by counting the leading zeros of M, or mathematically the formula is as given here. And then we simply take k coin flips from our entropy source. We consider these to be the bits of a random integer z prime, and then m prime 2 to the k is the range over which z prime ranges. Then we can recycle this state into our global uniform state using the recycling procedure. And after doing this, we've ensured that m is in this range. These methods that we've looked at for randomness recycling are widely applicable to a number of different sampling algorithms. For example, for uniform distributions, we can improve the basic division method as well as more advanced recent methods, such as Lemire's method, which replaces division with widening multiplication to speed up runtime, as well as Bracker-Rosinski and Lemire's method, which uses widening multiplication as well as batching to further improve entropy efficiency and runtime. Our randomness recycling also applies to those samplers for general distributions, non-uniform samplers, including inversion sampling, lookup table sampling, alias sampling, and DDG tree sampling. Now we'll take a closer look at the uniform sampling procedure. Here, the input is this uniform random state carried over from the previous round, as well as coin flips from the entropy source. And our desired output is a uniform over a specified range Ni, and we will also be producing this recycled uniform random state. So we can describe the problem as follows. We want to generate a uniform over a given range N, and we can assume that we're given a random state Z over M outcomes, where M is at least as big as N. If this wasn't true of the input random state, then instead we can just draw extra coin flips from the entropy source using that refill procedure that we saw before, and that refill procedure will allow us to guarantee that M is large enough. And now I'm going to work out an example on the whiteboard showing how we can do this kind of division method to generate a uniform. So let's say that we have a goal, generate X uniform over the outcomes 0, 1, 2. This corresponds to N equals 3. And say we are given Z uniform over 0, 1, etc., 13. This corresponds to M equals 14. Yeah?
Actually, not for a bit. You went from D to N. Like N was the number of samples. Your D. This was your D from before.
Roughly.
Like basically, I should think of like this as like D equals 3, and then P1, P2, P3 for the over.
Yeah, you can think of it like that, I guess. And so here, I will just write out the possible values of Z. We can consider Z equal to 0, 1, 2, or 3, 4, 5, or 6, 7, 8, or 9, 10, 11, or 12, 13. So here I kind of grouped them into groups of 3 to show how we're going to get this target uniform over 3 outcomes. We'll group these 0, 1, 2 together, and similarly for the remaining groups of 3. And so, for example, if we have Z equals 4 as our choice, then we can number the values within this group as 0, 1, and 2. And therefore, if we want a uniform over this set of 0, 1, 2, we'll return just the value 1 corresponding to this 4. So we'll return X equals to 1. As another example, if we had Z equal to 9, then we can again number this group as 0, 1, 2, and with 9, we'll be returning value 0. So Z equals 9 means X equals 0.
Should that be U, is what you have on the slides?
Yeah, that's right. This X is the same as U. And for our last example, we have this 12 and 13, which don't form a group of 3. So if we just had Z equals 12, then we cannot return a value, and instead we just need to reject and repeat. We'll need to draw a new uniform input and then try again this whole procedure.
But you had information, because that would also have happened with 13.
Yeah, that's
So
right.
there's a little bit of information there.
That's correct. One general thing you can see about this procedure is that the value that we're returning is the remainder of Z mod 3. Z mod 3 is equal to 0, 1, 2, 0, 1, 2, 0, 1, 2, 0, 1. So in fact, some inexact uniform sampling algorithms will just return this remainder in any case. They would return 0 in this case, but then the value, the 0, 1, 2 they're returning is not exactly uniform. So exact uniform samplers using the division method will need to reject in this case. But, yes?
Yeah, I'm a bit confused by when you say that they have to reject, taking what Daniel is saying. Like, if instead of 3, for example, this was some large number and your kind of remainder was inexact, but off by 1, it feels like you would be throwing away quite a bit of information.
Yeah, that's true. You are throwing away information, but there's not a way that you can use it.
That's like a provable fact, or
at least without like carrying it around to the next round. But if you're not doing any randomness recycling, then these are already grouped together, so you can't like try to group with any of them, and you don't have at least 3 outcomes here. So whatever you're doing, you'll need to like draw extra randomness in order to be able to produce a sample if you fell in either of these cases.
Right, so yeah, I agree you need extra randomness, but you not necessarily need to forget like which, and perhaps this is also like part of what you're doing against.
Yeah, that's true. That's exactly what I'm going to talk about right now, is how we can add randomness recycling to this basic division method uniform generation procedure.
Okay, we also have extra information about which group was chosen.
Yeah,
If you
that's right.
generated, yeah,
Mhm.
okay.
Yeah, so we have these groups here. We have group number 0, 1, 2, 3, we can call them. So we have 4 different possibilities. And another thing we can note is that you get these numbers by taking the floor of z divided by 3. So like this value we were returning was the remainder, and this group can be given by the quotient from integer division. And given a particular value of x that we're returning, like in this case where we had x equals 1, there was also a case in this group where we had x equals 1, and a case in this group, and a case in this group. Therefore, this 0, 1, 2, 3 possibility is uniform and independent of this value of x. Therefore, in this example where we had z equals 4, this 1 is a recyclable value. So we can update z and m gets 1 uniform over 4 outcomes. Similarly, in this case where z was equal to 9, we can update z and m to be this number 3 uniform over 4 outcomes. Lastly, in this reject case, we could not return the value x, but we can still recycle this uniform. We therefore can update z m gets the values 0 uniform over these 2 different outcomes. Cool.
So right now you're like solving a problem that's independent of the input distribution's PI, right? You're just solving the problem of generating uniform samples from some intervals 1 by 1. Like
that's
this,
correct.
this has nothing to do with the PIs yet.
That's right. Yeah.
Okay.
It's in that diagram as we saw.
You're doing the uniform box on the very left, right?
Yeah, it's just that uniform box.
Okay.
But this is, yeah, the whole idea of randomness recycling is that we can recycle this group, and we can recycle this information in the reject case, and we can return a value in these accept cases. Are there any other questions about this? Okay. Now we'll get into the more general formulation of this. The method of integer division will scale an integer z to a given range n by computing this quotient and remainder, as shown in this diagram. So our accept case is given by the quotient from z being less than the quotient from m being divided by n. And in this case, we see that the remainder is uniform over these outcomes, 0 through n minus 1, and further, the quotient is uniform over the outcomes from 0 to qm minus 1, and these two are independent. Therefore, in the accept case, we recycle this quotient because it's over this kind of arbitrary range qm, and we return the remainder, rz, which is uniform over the range that we want. In the reject case, as we said before, we simply recycle this remainder and repeat. One thing we notice is that the only entropy inefficiency of this algorithm is in this accept-reject decision, which kind of loses some information over here. And therefore, we want to minimize the rejection probability in order to have a better entropy efficiency. And the way we do this is make m large. And when m is large, then this rejection probability can be driven to 0, so we buffer extra coin flips. And the nice thing about this is for every additional coin flip we buffer, we cut the rejection probability in half, while we only increase the number of bits we need to store z and m by 1. This is what gives us the kind of logarithmic dependence on 1 over epsilon and the exponential improvement compared to previous work.
But does your choice of m, like, do you need to know the future PIs?
No. Or you only need it for, it only depends on this PI. That's what the uniform range depends on.
But I guess if I sample m really large, then I'm gonna have a bunch of randomness going into my next round. Right?
Mm-hmm.
But what if that next round, the new PI is just like, you don't need that much randomness.
Mm-hmm. That's why you'll just like keep recycling it from round to round.
But like, what if it just
this is the
terminates that?
constant term that we saw, where we had plus epsilon plus another constant. That constant is the size of this integer.
The log d over epsilon?
Yeah, that's right.
Okay.
So an imperative implementation is as shown here, where we just have a simple loop and these integer divisions and the accept and reject cases. So this is quite simple to implement. Next, we'll consider the non-uniform sampler, and in particular, the inversion method. Here we're converting a uniform sample into the non-uniform sample from the desired distribution, and we'll also be recycling this uniform state. So we can assume we're given a distribution with integer weights, a0 through an minus 1, and we use big A to represent the cumulative sums, or prefix sums, of these weights. The inversion method converts a uniform over the weight sum into an exact sample from the desired distribution. In this example, we have 3 outcomes with weights 2, 5, and 3, so we want to generate them with probabilities 2/10, 5/10, and 3/10. The way we do this is by taking our uniform U, as shown in this top row, and comparing it with these prefix sums of the weights. Then we have 2 possibilities that give outcome 0, 5 possibilities giving outcome 1, and 3 possibilities giving outcome 2. The way to compute this is binary search, which only takes logarithmic time, assuming you have access to these cumulative weights. And another thing we can notice is that conditioned on a particular value of x, or a color in this diagram, we have a uniform over these cells. And if we shift it by subtracting off the previous cumulative sum, then we have a uniform over the range from 0 to the given weight. Therefore, we can recycle this uniform and return this non-uniform sample value. This whole procedure is entirely reversible. The information contained in this input uniform is the same as the information in the discrete sample paired with this recycled uniform value. And therefore, the entropy efficiency of this non-uniform sampler is exactly the same as the entropy efficiency of the underlying uniform sampler that we needed. So we can also implement this quite efficiently, as shown here. Next, we'll consider the alias method, where again we have a uniform input and want to generate this non-uniform output. But in comparison to the inversion method, the alias method removes the log n overhead from binary search. And instead it uses a constant number of operations at sample time. And it only requires linear space and pre-processing. The basic idea is as shown here. We consider the example where we want a probability distribution where A should be generated with probability 2/5, and B, C, and D each with probability 1/5. The first step is to pre-process and create this alias table as shown on the left. This is considered to be packing the probabilities into a rectangular array such that the number of cells with each outcome is proportional to the probability of that outcome. And we can also note that each column is is guaranteed to only have 2 different outcomes in it, which is what allows the linear representation. And to sample from this table, all we have to do is generate a uniform index into the table and return the sample at that index. For example, if we have column 1 and row 2, then we're in the cell A5, so we'll return the value A. And our addition with randomness recycling simply tells us that we have this 5, which is uniform over the 8 different cells that are labeled A. And the extra data structures we need for this recycling are also just linear space. Therefore, our recycled method achieves the same space and time complexity as the original alias method, while also coming epsilon close to the entropy rate. This concludes our technique section, and now we'll talk about some results. Steven?
Sorry, quick question. What is the point of the preprocessing if you only see each distribution once?
Yeah, it's more in the practical case, like if you're considering you have some random number generation library, maybe the user will create this data structure and they know they want to create multiple samples from it.
Okay, but it has no benefit in the online setting.
That's right, if you're never going to sample from it again. So here we have plots showing the pre-processing time, entropy usage, and sample time for different algorithms. We'll represent the randomness recycling version in orange and the baselines without randomness recycling in blue. Here's the alias method that we just looked at. We see the pre-processing time is slightly larger because we need the extra array. However, the entropy efficiency is much better, which translates also into sample time improvements. We can see this same trend in the other methods, for example, the binary search inversion we saw before. Actually, we don't require any extra pre-processing, but we similarly have better entropy and runtime. Yes?
What's your experimental setup? Like, what are these plots like?
This is just a collection of different distributions with weight sum 10 to the 5 and a different number of outcomes n. So from left to right, you're getting like, more and more outcomes in your distribution.
So each dot is a different distribution.
That's
set.
right. Mm-hmm.
So this is like a performance plot, basically. It's like
Yeah. But they're kind of generated randomly, so the entropy isn't like a linear function of them.
and your experimental setup is like you just took a single machine. What machine were you doing this on?
Just from my computer.
Oh, you ran it on your computer,
Mhm.
and it's I see. And did you like was it like a Python or like what was implemented in?
C. Yeah.
What is the baseline implementation?
The baseline implementation for the alias method is just, I think, translated from Rust to C, like pretty directly. Just, their typical implementation. These are pretty simple. They're pretty close to actually just the pseudocode that we saw before, where the pre-processing corresponds to like making those prefix sums or making this alias table. Yeah. But yeah, we're just using the same data structures for each. And yeah, we have the same trend for the lookup table inversion and also for DBG tree sampling. One nice thing you notice in all of these plots is that we're using the same distributions, so the entropy consumption of our randomness recycling method is pretty much the same on all of them, because we come like within 1/1000th of the entropy rate, whereas the other methods do not. Another application of our method is for arbitrary samplers. Here we considered the discrete Gaussian. Yeah, Bill?
Oh, so just for interpreting the previous slide, or I guess more than one slide, okay. So should we interpret this as saying that in practice, for real world samplers, that even if you don't really care about the entropy usage, we're just getting a real world time improvement?
Yeah, that's correct.
Okay. And is it true that the real world samplers don't really care about the entropy usage, they just care about the time?
I guess so.
Okay.
Okay. So here for this discrete Gaussian sampler, their baseline is shown in blue and our method is shown in orange. We achieve a roughly 8 times improvement in this entropy consumption. And we did this by just randomness recycling their primitive samplers they used. They defined this discrete Gaussian sampler in terms of uniform and Bernoulli, and we just recycled these two and didn't do any extra complicated recycling, like related to the nature of the distribution. But even with just this simple trick, we're able to get significant improvements in entropy efficiency. And this shows kind of the generality for, yeah. One last experiment we'll look at is the Fisher-Yates shuffle. Fisher and Yates showed that if you want to generate a uniform permutation of an array, then it suffices to generate a series of uniform random numbers and perform swaps based on where the index depends on what those uniform random numbers were. And in some recent work, Brackett, Brzezinski, and Lemire showed a highly optimized uniform, which allows them to get state-of-the-art performance on a given permutation benchmark. And here we see the blue is this baseline, it's the division method that we saw without randomness recycling. The red line is our division with randomness recycling. Green is their highly optimized method, and yellow, or this orange line, is our method which combines randomness recycling as well as their optimizations using multiplication instead of division and batching together uniforms. So yeah, we see that our methods can be very fast, especially for this uniform generation case. And now we are ready to discuss some of the future work, which has not yet been presented at SODA. At SODA, I gave this as a conjecture, but I've now proven it. So the statement is as follows. Any online random sampling algorithm, which comes epsilon close to the entropy lower bound, requires at least log 1 over epsilon bits of space for its auxiliary state, which is carried over between samples. And to compare, our method uses asymptotic to 2 log 1 over epsilon bits of space. So if we ignore the fact that our method we showed only works for rational distributions with bounded denominator, then we can say we come within a factor of 2 of the absolute optimal space for a given epsilon. And the proof of this is quite complicated, but for a very brief sketch, we just consider an arbitrary algorithm, and we show that after going through all of the different states in the state space, you end up losing 1 bit of entropy if you're sampling from low entropy distributions. And therefore, if you want this to be epsilon bits per sampling round, you'll need a large enough state space. And that's given by this log 1 over epsilon. Some future work would be to tighten this entropy space trade-off. The theorem I just showed only works if you're allowed to have arbitrarily small probabilities, and it would be interesting to see if we can prove it also for the case where we restrict to rational distributions with bounded denominator. Another line of work is improving the upper bound, where we showed that we have 2 log 1 over epsilon possible. If we instead use non-uniform states with clever encoding, then we can get asymptotic to log 1 over epsilon. However, this seems to be difficult to implement and might not be as practical, but yeah, it's an open question of whether this non-uniform states could be actually useful, or if it's just a mathematically nice result. And related to this, we can also consider when we don't just have this bounded space for our algorithms, and instead we allow dynamic scaling. For example, for our uniform states, if we allow these uniform integers to get bigger and bigger over time, if they scale logarithmically over time, then instead of this epsilon n, we can achieve O of log n in the best case. And if instead we're using non-uniform states, we can get to O of 1, which will give us some true interpolation between Knuth and Yao's absolute optimal method and stateless samplers. Another line of work is to improve the more general protocols given by Kozen and Soloviev. They considered the case where your input distribution is not necessarily a fair coin, but instead could be an arbitrary discrete distribution. And they also considered when the output that you're sampling from is or has irrational probabilities. We are currently working with, collaborating with David Harris to work on algorithms sampling from computable real CDFs, and we can achieve a similar exponential improvement compared to Kozen and Soloviev's protocol, just in expected space instead of actual space. We can also apply our methods to get exponential improvement for the discrete rational to rational case. However, we can also combine these two methods to get an expected log 1 over epsilon real to rational conversion, but it's still an open question. We're thinking about whether we can get true deterministic O log 1 over epsilon conversions from real probabilities to rational distributions. And in addition to this theoretical future work, we're also interested in some applications. Perhaps the most promising application of this entropy-efficient online random sampling is for true random number generators. True randomness is defined as randomness from physical sources, and it is often quite expensive. For example, the website random.org has an array of radios which detect atmospheric noise and convert them to random bits, but their rate is only roughly 12,000 bits per second. They provide this randomness through an online website service where you can specify a range of integers, and they'll give you a uniform sample from that range. Furthermore, your uniform sample will be independent of all previous samples you've been given, as well as all samples anyone else in the world has been given. And that kind of shows you why it's important to conserve these random bits, because you cannot generate them too fast. And our techniques would allow you to build an efficient service like this where the users are also allowed to specify non-uniform distributions they want samples from. To conclude, we have introduced the online random sampling problem.
Wait, I thought your algorithm was also like best even if the distributions were uniform over some range.
Yeah, that's right. But we can we can improve even for the discrete case.
But just you can also just improve straight up this one. Okay.
And the second point is we have an exponential improvement in this trade-off in entropy and space, as well as our randomness recycling methods using these uniform states are quite efficient to implement and can improve the real-world runtime. Thank you for listening.